some maybe slightly more advanced, slightly more recent problems and results, and give you some idea of some of the where combinatorics is over the last 10 years or so. Well, at least one part of it. So to start, so there's going to be, I guess, two halves to today's class. The first half I'll tell you a result actually from the 80s, but using the regularity lemma. The proof is very nice and simple, but the technique has proved to be quite powerful since then. And then I'll tell you in the second half about some an extension of that result and many other results that we've learnt about which have happened in the last 5 years or so. Anyway, so let me tell you about so here's a question. So how many graphs are there on n vertices which are H-free? Okay. So H is some graph, and I want to know how many graphs on n vertices don't have a copy of H. So give me a lower bound. Well, what do we know about graphs that are H-free? We know the extremal number of H is equal to 1 minus 1 over chi of H minus 1 plus little o1 n choose 2. This is Erdös-Stone. Okay. So we know that there exists a graph which has no copy of H and has about this many edges. And what is it? Well, it's the Turán graph on TRN, where R equals chi of H minus 1. Yeah? If R is 1 less than the chromatic number of H, you take an R-partite graph, then it's H-free. This is H-free. Why? Because a copy of H inside this graph, putting it inside means R coloring the vertices. It means doing a proper R coloring. Right? If you find a copy of H in here, where is it? It's here. This is like 3 coloring the vertices of H with no edges inside the color classes. But it's not possible because I chose R to be chi of H minus 1. Okay. So there exists a graph with that many edges. So how many graphs have no H? Well, each edge you can either keep or not keep. This implies there are at least 2 to the power extremal number of H, which is basically 2 to the power 1 minus 1 over R n choose 2 graphs. Right? How do you find an H-free graph? Well, one easy way is take an H-free graph and take any subgraph. There's this many. The famous conjecture of Erdős from the 60s, I think, that says for every graph H, okay, it's not quite true. I think there's a few exceptions which are, so some forests don't work. Let's say with a cycle. the number of H3 graphs on n is equal to 2 to the power 1 plus little o1 times the extremal number of h. Okay. So it's not true that, not necessarily true that almost all look like this, but this is sort of the main contributor to the number of H3 graphs. That the others, that they at least add something just small to the power. This is, well, it's still open for almost every bipartite graph. But for non-bipartite graphs, there's the following theorem. It's the theorem of Erdös-Stone and Rödel from, I think, 86 or something, that says that number of H3 graphs is 2 to the extremal number nh plus little o n squared. Okay. So this proves the conjecture whenever the chromatic number of h is at least 3. Because if the chromatic number of h is at least 3, then the extremal number is quadratic, and so little o1, the extremal number, is the same as little o(n) squared. But if h is bipartite, it tells you basically nothing. Okay. So this proves the conjecture if the chromatic number of h is at least 3. Okay? So let's prove this theorem. Proof. I'm going to use the so-called stability method. Which is well, once you see it, a pretty simple idea, and it's turned out to be pretty useful. So it's worth knowing. Okay, so what is it? Is the statement okay? Everything fine so far? No problems? No confused faces? Okay, good. So I think Gonzalo taught you the Erdős-Simonovic stability theorem. Maybe. Possibly? Okay. Well, we'll see. Let me at least do it for triangles. Let's say. So it's for every beta, there exists an alpha such that if G is, well, say k r plus 1 free. So I guess also for every r. So if there's no copy of the complete graph on r plus 1 vertices, then either the number of edges of G is at most 1 minus 1 over r minus alpha times n choose 2. So it's smaller than the Turán number by a positive fraction. Or G is within beta n squared edges of being r partite. What I mean is there exists an R partition of the vertices such that inside the part there's a most beta n squared edges. Okay. So there are very few edges inside the parts. Right? Almost all of them are between the parts. Why is the stability theorem? Well, it says that if you've got no kr plus 1 and you're anywhere near the extremal number, you have to basically look like the extremal example. The extremal graph is the Turán graph. It says if you're even close to it, then you have to look from a distance like the Turán graph. Okay? You have only very few edges inside the parts. Have you seen this before? Or no? Okay. So to prove this it's not easy, but it's not for a triangle at least, it's not very hard. So this is can be a difficult exercise to go and prove this. Okay, so we're going to use this theorem together with the regularity lemma to prove the Erdős-Frankel-Rödel theorem. Okay, so proof of Erdős-Frankel-Rödel. So, let G be H free, and let chromatic number of H minus 1 equal R. Okay. So, 1. Apply the regularity lemma to G and form the reduced graph. So first I should say, what are we going to do? We're going to try and prove that the number of H-free graphs on n vertices is at most the extremal number plus some small constant times n squared. Okay? So we have to pick a small constant first, and then I'm going to pick a beta sufficiently small. Okay? It's important this works for every beta. Okay, so the final constant that's going to go in here will be, I don't know, 10 beta or something. Okay? And when I form the reduced graph and when I apply the regularity lemma, I have to pick a delta and an epsilon. Right? So they're going to depend on this beta. Okay, so really I should be saying, first pick some constant we're going to get, let beta be sufficiently small, let delta be sufficiently small, and then let epsilon be sufficiently small. But I'll leave that to you to fill in the details. Okay. I want to give you the feeling of the proof. Because this is how you should think about proofs using the regularity lemma. Okay. I don't want to get lost in different small constants. Okay, so you apply the regularity lemma, as always. You form the reduced graph, as always. What do we observe about the reduced graph? We know that G is H-free, so R is... So it's definitely H-free, but even more, what does it also avoid? So you're completely right, but we're going to use something even stronger. Clue is over there. Right. It's KR plus 1 free, right? If there's a KR plus 1 in your reduced graph, then we can use a slicing lemma to find a copy of H in, well, not R, but also where all the edges correspond to H are epsilon, delta. Good. and then we can find by the embedding lemma. This is by the embedding lemma. So if there's a copy of kr plus 1 in our reduced graph, by the embedding lemma, there's a copy of h in G. Okay. Okay. So now we can apply the stability theorem. So by the stability theorem, by the ES stability, this implies that either one of these two holds. Either R has at most 1 minus 1 over R minus alpha k choose 2 edges, or R is beta k squared close to being R partite. Okay? So, this is the stability method. And now we're essentially done. All we have to do is count the number of graphs in this case and the number of graphs in this case, and both times they'll be small. Okay? So, are there questions about the stability method? I did it quite quickly, so it's okay to have questions. We just apply the regularity lemma, as usual, with some tiny epsilon. We form the reduced graph, which is the pairs which are epsilon regular and have density at least delta. We observe that by the embedding lemma, if you had a copy of kr plus 1 in your reduced graph, then what could you do? You draw a picture. If you had a copy of kr plus 1, so this is kr plus 1, r I guess here is 2, then we could slice it up into pieces. By the slicing lemma, which was our, I think, property 2 of epsilon regular pairs, every pair here is, well, not quite epsilon delta, epsilon regular, but epsilon divided by, times the number of parts. So then you have a bunch of pairs. You have a complete, so a blow-up of a complete graph with every pair epsilon regular, and then apply the embedding lemma to this graph to find a copy of H. Well, there's a copy of H inside here if T is sufficiently large, and therefore there's a copy of H inside here. Okay? Good. More or less. Okay, but then if R is kr plus 1 free, then we can apply this theorem to it. And we know to R. And we have two possibilities. Okay, so let's try to count. So, A. How many graphs G such that the edges of R is at most 1 minus 1 over R minus alpha times k choose 2. Okay. How are we going to count that? Well, the first thing we have to do is choose a Szemerédi partition. Okay? So there might be quite a lot of ways of doing that. But how many? Well, for each vertex, you choose one of the parts. So there's k parts, so it's only k to the n. That's the number of choices for the Szemerédi partition. And now, given a Szemerédi partition, we should choose the graph R. Well, that's easy. That's just 2 to the k squared at most. K is just a constant, right? So these things are all tiny. And now we've picked the graph R, well, we should choose the edges of G. So for each edge of R, then how many choices do we have? Well, it basically could be a random graph. Right? It could be anything. So for each edge of R, we have something like, well, how many edges of G are there? As many as n over k squared. Okay, so this is R. This is n over k vertices, n over k vertices, n over k vertices. For one of these, we have to pick the graph here. The number of choices is 2 to the n over k squared. N over k squared edges, each can be there or not. And we do this for each edge of R. And then finally, we choose the rest of the edges of the graph G. But remember, there aren't that many of them. Or there aren't that many choices. There are the non-regular pairs. There are the sparse pairs, and they're the edges inside parts. So there are at most 2 delta n squared edges. So we can just multiply something stupid. N squared choose 2 delta n squared. Okay. So this, I claim, is an upper bound on the number of graphs which have, well, actually, the number of graphs in general. Is that okay or not? So what did I do? First, I chose the partition. Then I chose the reduced graph R. Then I chose the edges of G which contribute to edges of the reduced graph. And finally, I chose all the rest of the edges. Okay? I feel like this is n choose 2 delta n squared. Okay? And every graph, not even every H3 graph, every graph looks like this. So, if the number of edges is at most this, then we just plug it in here. Yeah, this is at most. So these terms are both tiny. They don't really matter. And this term is something like 1 over delta. So what is it? So just using our normal upper bound on binomial coefficients, it's this, right? And to take care of these two terms, I'll just stick a 2 in here. Right? So 2 to the delta n squared is much bigger than this. And then this term, if I just substitute in, it's 2 to the n over k squared, 1 minus 1 over r minus alpha, times k choose 2. Let's cancel these n squareds. And now, because I chose delta much smaller than alpha, this alpha term beats this term completely. This is at most 2 to the 1 minus 1 over r minus alpha over 2 times n choose 2. Which is even better than what we hoped for. You're all looking extremely unhappy. So, you should tell me at which point you became extremely unhappy. Was this part okay? It's the calculation you don't like. Yeah. Okay, so somehow this shouldn't be the hard part, because this is just counting. The hard part's over there. That's all the cleverness. Whereas, but it's something about maybe there's just too many numbers around. It's hard to take in. But really, we didn't do anything here. We just counted. And we counted in the stupidest possible way. What we know is we have a Szemerédi partition, and we have a reduced graph, and then we have very few other edges. Why do we have very few other edges? Well, the same reason as always. They're either in irregular pairs, or sparse pairs, or inside parts. So, okay, let's do the 4 things one by one, and you can tell me which one you're not happy with. Is this okay as a bound on the number of Szemerédi partitions? Each vertex, you pick one of the k parts. Yeah? K to the n. Now, we pick the graph R. Well, it has k vertices. So each is k choose 2 if you like. Each pair of parts can either be in R or not. An edge of R or not. Okay. This term is just a constant. It's nothing. This is the really important one. For every edge of R, this is an epsilon regular pair with density at least delta, we have to choose the edges of G. Okay, so we choose which edges with a vertex here and a vertex here are in G. There's n over k times n over k such pairs, and each one is present or not. So we have 2 choices for each possible edge. Either it's an edge or it's not. It's just the same thing I said here. It's exactly the same. Right? You just pick an arbitrary subgraph of the complete bipartite graph. And you do that for each edge R. Each edge of R. Okay? So this is the number of choices, edges of G, which are in between pairs where the edge corresponds to an edge of R. Okay. And then finally, there's a whole bunch of edges we haven't looked at yet, but by the regularity lemma, we know there's very few of them. At most 2 delta n squared. Delta n squared from sparse pairs, epsilon n squared from irregular pairs, and epsilon n squared inside parts. So we can just put them anywhere. There's so few of them. So just pick any edges you like. Okay. And that's chosen the graph G. There's no more choice to make. Still unhappy. More happy. Okay, so then we're done. Right, so then the rest is just use the approximations that we've always used. So the binomial coefficient. So it's at most this, without the 2. These terms are both tiny. Right? This is exponential, this is constant. So they're definitely much smaller than something to the power n squared. Right? They're completely irrelevant. And then what's this term? E n choose 2 over 2 delta n squared. The 2 delta n squared. Cancel the n squareds. You get 1 over delta to the n squared. When delta gets really small, this one matters more than this one. Right? So it's like e to the delta log delta. And if the number of edges of R is at most this, we get this. Well, the k's cancel. So we're going to get 1 minus 1 over R minus alpha n choose 2. I lost a little bit here to deal with this term. Because delta, we can choose delta as small as we like. Right? So remember, in the stability theorem, we said for all beta there exists an alpha. So what do? We pick beta, really, really, really small. That then gave us an alpha, much smaller. We then chose a delta, much smaller than that, and an epsilon, much smaller than that. Okay? We applied the regularity lemma with that epsilon. And we formed the reduced graph with that delta. Okay? So the order of constants is like this. We're going to pick beta much smaller than 1. Okay? So this is, you just have to remember the order, right? There's nothing complicated. Okay? So because alpha is much bigger than delta, we pick them in this order. Because alpha is much bigger than delta, then this alpha completely kicks the ass of this delta, right? Even though it's 1 over delta to the delta, doesn't matter. Okay, so we get something much smaller than what we want. Okay, so that's one of the two cases. The other case how many graphs G have an R which is right. So the other case is that R is very close to being R-partite. What does that mean? It means that there exists an R partition of the vertex set such that inside the parts there are at most beta k squared edges. Okay? So there are very few edges inside parts. So this can be as dense as you like, but in here it's very sparse. Okay, how to count in this case? Well, start the same way. K to the n choices for the partition. 2 to the k choose 2 choices for R. And now what? So between the parts, you can do anything you like, right? So these are these are partitions of. This is a partition of the graph R, but that corresponds to a partition of the graph G, right? What you're doing is putting a whole bunch of the Szemerédi parts all clumped together. You're saying there's at most beta k squared edges of R inside here. But what does that imply about the number of edges of G inside here? Well, it's at most. Okay, well, the edges of R can contribute n over k squared. And all the rest can contribute 2 delta n squared. This is at most 2 beta n squared. Edges of G. So I claim that what we have is not just an R partition of R. No? So let me write something else perhaps about this. I claim that we not only have an R partition of the graph R with few edges inside each part, we have an R partition of the graph G with few edges inside each part. Because almost all the edges of G, all but 2 delta n squared of them, correspond to edges of R. By the same calculation we always do. So the only edges inside this part, well, not only, apart from a few, correspond to edges of R. There's almost beta k squared times n over k squared of them, which is beta n squared. And this beta n squared is bigger than this, right? Because of the order of constants. Okay. So what we have is an R partition of G that with almost 2 beta n squared edges inside each part. So, in fact, we can do even better. So we pick our R partition, that's R to the n. We pick the edges between the parts. That's 2 to the power the number of choices. So the Turán number of n at most. The number of edges in an R partition, an R partite graph. And finally, we choose the edges inside, which is the most n choose 2 beta n squared. For the same reason. Just throw 2 beta n squared in any way you like. Does this make sense? So the claim is G is within 2 beta n squared of being R partite. The claim it follows from the fact that R is close to being bipartite, R partite, that G is. And the proof is just what I said. All but 2 delta n squared edges of G correspond to edges of R. Okay, so now we choose the R partition. Each vertex pick the part. Choose the edges between the parts, which is most 2 to the Turán number of n, and then pick the rest of the edges. Okay. That's at most. Do the same thing as before. E n squared over 4 beta n squared to the 2 beta n squared. Sorry. R to the n is tiny and doesn't matter. Stick a 2 in there. And here we have 2 to the 1 minus 1 over r n squared, basically. So now we get something that really is bigger than 2 to the extremal number of h, but only by a little bit. So again, we can cancel the n squareds. We get 1 over beta to the beta to the n squared. So if we chose beta sufficiently small in the first place, this makes this term as small as we like. 2 to the, I've run out of letters, so beta prime n squared plus 1 minus 1 over r n choose 2. Okay. Which I guess you can rewrite as extremal number nh. Okay. So this part contributes the extremal number of h, and this part is just error, where this beta prime we can make as small as we like by taking beta small. Okay. Done. So these two blackboards, if you didn't like them, don't worry about it. The proof was here. So over there I just maybe hopefully convinced you that we really had proved it, but we'd proved it at this point. Right? This is the proof. Apply the regularity lemma, observe that R is KR plus 1 free by the embedding lemma, and apply the stability method to R. So it's the same thing we did with the 5 steps that I wrote down. You're just applying some standard theorem to the reduced graph. Okay. And then you do some counting, which, whether you believe it now or not, really is easy. You just count. This is the hard part. Okay. So, let's take a 5-minute break, and then afterwards I'll give you a brief introduction to doing extremal results in sparse random objects. Any questions?